Jim McGregor from TIRIAS Research here at Embedded World, and stopped by my first booth with, I have to admit, a very good friend of mine, Nandan, who is the Chief Commercial Officer of Baya Systems. And it's a really interesting company because they're addressing one of the growing issues as we go to this chiplet environment, or chips of chips environment, if you will. So Nandan, tell us a little bit about the problem and what Baya Systems is doing to solve that as we go forward.
Well, firstly, Jim, great to see you as the first guest I have at our booth at Embedded World. So Nandan Nayampally, as Jim mentioned, Chief Commercial Officer of a startup called Baya Systems. We recently raised our Series B round with Matrix, Maverick Silicon, Intel Capital, and of course a strategic investment from Synopsys. Now, Jim, you've been at MWC last week. Obviously the key problem was not compute anymore. It's really about the network. That's where the efficiencies are. That's where the power is spent. And finally, especially with AI, it's really about the data. And data movement is the real problem.
Yeah, we're going to a densification of computing with very high performance solutions and being able to transfer data efficiently and quickly. And if you can't, the problem is a lot of these solutions now are only running at about 30% efficiency ratings because they just can't transfer the data quick enough.
Indeed, and in fact, the problem is continuing to grow. If I look back at 10 plus years ago when ARM was looking at the server problem, it was this distribution of compute because big iron was being limited by data movement. So as compute got distributed, so also the pressure in doing more intent and condensed networking to bring all of these components closer back. Baya actually kicked off 2 years ago, knowing that the problem with today's solutions is that they are not ready for that scale, they're not ready for chiplets, and really that's where the densification, as you call it, is really kind of manifesting itself. Today, if you look at even Graviton type servers, you're talking about maybe 48 core, 64 core on a single die. Great, they're connected by a single network. But in the next generation, you're going to be actually not just doing more cores, but different types of components tightly coupled together. And for that, you need not just a standard type of fabric, but a fabric that can transport different types of protocols while minimizing the amount of blocks or components that are built into it. Now, add to it the problem that some of these fabrics are not aware of what happens when they grow across different chiplets, and chiplets being a way to both reduce the yield problem, but also then scale best-in-class solutions which you can mix and match, then the problem gets a lot more complex. And so what we've seen is really the need for a fabric solution, a system solution that can scale not just a single die to lots and lots of different connected components efficiently, but then enable larger systems to be built with not just system of chiplets, but then systems of chiplets that can actually come together into much more dense, much more efficient systems. What Baya does is actually provide a top-down kind of software-based, software-driven, and a data-driven analysis that allows you to kind of understand traffic top to bottom and actually build both the architecture, the partitioning for single dies across multiple dies and multiple chiplets, and then of course build the fabric that is needed to service those systems. One of the products we announced recently, literally just a week ago, is a product called NeuroScale, which is really addressing the switching problem that's coming together. You've seen the NVIDIAs of the world talk about NVLink. You've seen standards like UA-Link come in that tie together much more capable accelerators much closer to the compute. Now, that's great, but then if you're trying to solve it by using brute force crossbars, which don't scale to the level of nodes, the number of ports, the number of actual connectors you need to put together, then that's where the bottleneck is. And NeuroScale is a focused solution that addresses that can arrange not just single chiplets, but scale switching to multiple chiplets and truly scale the density. We're talking about petabytes of data being moved. We're talking about 256 node solutions. So all of this comes together with a ground-up rethinking of how we solve that problem. That's what Baya does.
That's great. Can you kind of show us an example of that?
This is Dweeb IP. It's our list of products that we have together that solve coherent, non-coherent, multi-level coherent, which is needed as you go across multiple chiplets, and neuroscale type products. The key idea here is to pull together any type of key thing that we're going through, which is AI acceleration, data center, infrastructure type applications, automotive applications. All of them require much more advanced connectivity and networking. And that's what Baya kind of pulls together. So today, the data center is moving to scale out, which is kind of adding more capacity on the side. But really, scale up is where the performance challenges are, where you're actually trying to pull together much more tightly coupled acceleration that's going. What neuroscale does is that it allows you to scale much more compute, much closer together. And what we've seen is the crossbar problem today is that you can scale only to a certain amount of point and effectively need a lot more of the physical implementation challenges that crossbars hit. If you actually want to go beyond, you need a different solution. That's what neuroscale tries to do. And what we announced last week is fabric that can run 2 gigahertz plus while supporting very, very low latency, max latency across crossbar, any end-to-end, less than 20 nanoseconds. We're talking, in some cases, 13 nanoseconds. Very wide buses, in spite of this very low latency, and the ability to scale together, 256 chiplets, each supporting nearly 16 terabits per second of data, D2D. So effectively what you're seeing is a transformation of what you can see in the densification of networking solutions. Now, if we put it together, Baya is actually providing not just a fabric, but a system to analyze everything from system spec at a very high level, all the way to building the fabric, building the system, analyzing it, implementing it, and then also do post-silicon tuning. And the understanding or the underlying capability is our architecture, which is a very, very versatile network platform, which has petabytes of scale possible with the network. It's extremely flexible. It's not traditionally crossbar or ring. It's not just a tree network. You can actually really change your topologies. You can have a common architecture that can put together different types of fabrics, whether they be coherent and non-coherent. But all the time, it is data-driven, so you can analyze it, consistently update it, and when you develop it and put it out, it is de-risked, so simplifies your implementation and de-risks your time to market.
And these tools work with other EDA tool sets?
Absolutely. So that's a great question. This can be used in standalone mode, but that's actually to do the analysis. But really, it plugs into existing EDA tool flows and makes that progress much faster. The other thing to understand is you can get a little bit deeper into it. Really, you're looking at two software tool products, one to understand architecture and explore it, and the second one to build a microarchitecture, so they're Cache Studio and Fabric Studio. But underlying all of that is the fabric, which has a slew of different types of products, from protocol-free, which is used a lot in AI, high-performance AI, the traditional ARM-compliant AXI, non-coherent, the coherent ones. As you get into chiplets, you get into multi-level cache coherency, and then, of course, what we talked about was the neuroscale switch fabric. The one thing that we need to have throughout is not just for automotive, which is functional safety critical, but you're also seeing a lot of this in reliable solutions that are in industrial applications, in data center applications, in infrastructure applications, and we're designing this ground up to be both functionally safe and reliable. The key to all of this, of course, is having a fabric that has a common architecture allowing different types of protocols sit on top. This is really where the clear benefits and efficiency and scale come in. By having this common architecture, we can actually plug and play different protocols, not just the existing ones, but the emerging ones like UA Link, and consistently build fabrics that are more efficient, highly more performant, and at the same time not compromising on the KPIs and the metrics that you get. And if we put it together, this is really where the market is pulling us. Today, AI is growing, data movement is the clear problem, and what we're providing is fabric that can pull it all together. Much higher performance, much more capable, much more advanced capabilities like multicasting that simplify development of advanced AI solutions, and more importantly, keep them future-proof by having post-silicon tuning and runtime optimization. When we think about this from a multi-chiplet standpoint, we also need to understand that moving data across a single die versus multi-die is different. And you need to have a fabric and a system that understands those trade-offs. And this is why we've built our entire architecture to understand not just non-coherent traffic that goes across different protocols, but also coherent traffic.
So theoretically, how many chiplets could this scale up to?
So we are actually seeing, especially for switching fabric, up to 256.
Okay.
And that is the theoretical limit is actually not being hit. It's really more of the physical limits. Today we can see 130 based on the reticle limits of silicon and chips, but it's not too long before those catch up too, and you start doing even more chiplets in the same module. And so if we talk about chiplet readiness, because it's a very topical thing, we are a system that is ready for chiplets by having a chiplet ready network. We have the coherency and the non-coherency ready in the way we've developed our chiplet readiness. And then of course we have the software and the tooling that helps you analyze the partitioning. So we're addressing the issues from all aspects of building chiplet ready designs. So effectively what we're talking about is a complete solution that can help you design things that are ready for chiplets, pulling together not just high-level understanding, high-level capabilities, but helping you build the microarchitecture, set it up, implement it for very capable, scalable, dense solutions.
Cool. Thank you very much. When do we expect to see maybe this implementation on future designs?
So Baya has now multiple customers already signed. Some of them are in stages of actually going to silicon. We obviously cannot comment on their schedules, but you will see these solutions in the market within the next 12 to 18 months and ramping to production.
Cool. I look forward to it. Thank you, Nandan.
Thanks, Jim.